This is the solution that I can write down because I can integrate. The question over there?
Yeah, what do you integrate to?
Well, what I'm integrating is this equation.
Okay.
I integrate the top part up till TC, and I integrate the second part from TC onwards. From TC onwards, I start out at this value because I don't start out at N0 because I've already lost a bunch. Well, so you'll have to work through it and just see it, but that's conceptually what I'm doing. Whenever you solve an equation like this, if you start at a particular point, you say, what am I at this point? And then I decline exponentially thereafter. What's causing that exponential decline? Well, in the first part, just the natural mortality is causing the exponential decline. In the second part, the natural and the harvesting mortality is causing the exponential decline. Okay. Now I'm going to talk about the yield on 0 infinity. So how much yield do I get from the cohort? So this is the yield from the cohort. And there are two parts. The first part is that I don't harvest it initially, and I only start harvesting it at a constant rate at time tc. So how much yield am I going to get? Well, am I going to get any yield on 0 tc? I'm not. So I'm just going to get yield from time tc onwards. And I'm going to keep harvesting for all time into the future. And what is the rate at which I harvest the population? So what is the rate at which I'm harvesting the population? Well, it tells you in that red model number 2. I'm removing, yeah? Yeah, so this is just the harvest rate. So to get the harvest, I have to integrate the harvest rate. So I have to integrate V times N, but that would only give me numbers. I'm not only interested in numbers, I'm also interested in weight of each individual that I remove, because that gives me the biomass. So my harvest rate is Vn, but the rate at which I remove biomass is I have to take each N that I'm removing and find out what its weight is at the time I remove it to get the total yield. And that's from the cohort, and it's the biomass yield. So I'm looking at the yield of biomass from the cohort if I were to harvest it for all time into the future. And that's dt. Okay. And now if V is a constant, it can come out. And only this bit applies from time tc onwards. So I can take out, this is a constant, so I can take out n0 e to the minus alpha tc. And then I'm left with, this is the n part of it that I'm writing down here, this n part. E to the minus alpha plus v t minus tc dt. So that's the n part there. The v I've taken out, and I'm just left with the w of t. So this is going to be how I calculate my harvest. And this is my yield, y. And you can see that y depends on two different parameters that I can control in terms of fishering. I can choose the effort level v, and I can also choose the time that I start harvesting it, which is like selecting the gear. So if I choose a mesh size of a certain size, or hooks of a certain size, that only will catch individuals on a certain age, this is the knife edge selectivity assumption. We're going to throw that away later. It's not a great assumption. But just imagine that it works reasonably well. And by that I mean is that if I've got a net with a certain mesh size, all individuals smaller than the mesh size escape, and all individuals greater than the mesh size are caught. Yeah? Yeah. Why don't I integrate from 0 to t critical? Are you asking? Why do I take this out?
No, I'm talking about the value of t.
Why don't I have the 0, are you saying? Oh, this is, yeah, they shouldn't be. Okay, excellent. Yeah, that would confuse me too if I was looking at what I was doing. Okay, so now it turns out that if for w of t, well, it's not there. Where is my w of t? Okay, if I use the von Bettel-Landfried, if I put this in, I could actually do the integration. I'm not going to do it. But in 1954, there were two fishery scientists, Beverton and Holt, who did this, and they integrated this. We don't need to do that. We can solve this actually using numerically. We don't have to do the integration. They didn't have a lot of options to use numerical computers, so they actually put in the von Bettel-Landfried World Code, and they actually worked this out. But what I'm going to do is I'm going to do something else. I'm going to show you that this can be interpreted in a different way than what I have here. The way that I have it here is that I'm getting a yield as a function of v and a function of tc. So you have to agree that if I change v, so the value of this yield will change. If I change the critical size at which I get them, so the value of the yield will change. This is the yield from one cohort over its entire lifetime. Now you all get that. Is that right? Because we're going from tc to infinity. This is what I get from this cohort for its entire existence into the future. So this is the yield from one cohort over its whole lifetime. Now what happens if I have what is called a common pool? And at time 0, I get r individuals. And at time minus 1, I had r individuals. And at time minus 2, I had r individuals. And at time minus 3, I had r individuals. So in other words, it's now 2014. Let's say at the beginning of this year, r individuals came into my pool. Let's say at the beginning of 2013, r individuals came into my pool. They all come into the pool where their recruitment age is 0. So it's not their real age, but it's the age at which they recruited. And so I've got all these cohorts coming in from all time in the past. And as I go forward, at time 1, I will expect R individuals to come in. And at time 2, I expect R individuals to come in. And at time 3, and so on. But what's important now is just to consider this group of individuals that have come in for all times in the past. And I'm now going to harvest, I'm going to apply V over the interval 0, 1. So I'm now going to harvest for a year. Now, depending on if this critical size happens to be age 2, then I wouldn't catch any of these individuals over the year. And I wouldn't catch any of these individuals. I'd only catch these individuals and these individuals and these individuals. These individuals that I catch would be like, if this is 2, it would be like I'm catching this group of 2 to 3-year-olds. This group over here that came in 3 years ago, it would be like I was catching 3 to 4-year-olds. So you can see that if these cohorts are all identical, and they all were treated exactly the same way in the past, and they're all treated exactly the same way in the future, what I get from one cohort for all time by harvesting for all time, I get from all cohorts in a common pool harvesting them for 1 year. Because if they're all recruited a year apart, then these are the ones that were recruited 2 years ago, 3 years ago, 4 years ago. That would be that bit of the curve, that bit of the curve, that bit of the curve. Which is to say that YVTC is either the same as harvesting from one cohort over its lifetime, or harvesting from all cohorts under the equilibrium conditions that all cohorts were recruited at the same level and were harvested at the same way in the past. Who gets that? Who doesn't get it? So the rest of you are like in between. Okay, so let me bring up, can we get the lights there, some curves. So what you're going to have to do is you're going to have to think about this and keep thinking about it until it clicks in your mind. I understand it. And so let me repeat it. What is it that you've got to understand? That in this yield analysis, and this yield analysis depends on N0 here, so I can divide by N0. And if I divide by N0, then I get this yield divided by N0, which is R. So this is the yield per recruit. This yield per recruit from a cohort that starts out at a certain point and is subject to natural mortality alpha, and then from a critical point onwards is subject to harvest mortality V, and that critical point is time Tc. The yield per recruit is given by this expression. This expression says that if I come to a common pool and I have all the cohorts mixed, and all these cohorts started out with the same number, and they all had the same history of exploitation all time in the past, then over the next year, what I take from this common pool of cohorts is the same that I take out from any single cohort over its whole life. So this expression applies. So this is the yield per recruit in a common pool fishery for 1 year, provided the system satisfies the assumption that all cohorts in that pool have the same history of being recruited at the same level and subject to the same harvesting strategy, which is harvesting at a rate V from an age, from T subscript C units of time after recruitment. Okay, so let's see if I can now show you a couple of curves. So hopefully this will come up. Yep. So you can read about this, and there are two concepts here. So if we have a look at 9, the corresponding yield depends on the critical time and V. I can see I made V the second argument, not the first, but that doesn't matter. And I also introduced the catchability coefficient, which as I argued, you can put in or not, you can set equal to 1. If you have a look at the harvest you get, you can say, G, the yield per recruit. This is yield per recruit in kilograms per fish from a particular fishery, and on the one axis we have Tc, and on the other axis we have V. When you have a surface like that, you can also plot a surface in terms of its contours. So this is the highest value, this is a lower value, and on one axis you have V, and on the other axis you get Tc. And you can see there's kind of a maximum up here. So you can say, what is the best V and Tc? But you can look at the problem in another way, and you can say, if I select a particular Tc, then what's the best V? So if I fix Tc to a certain net size, then I can say, what's my best V? Or if I fixed, this is if I fix Tc, then I can say, what's my best, this is if I fix V, what's my best Tc? Or if I fix Tc, then I can say, what's the best V? So you can see I can fix one, and I can say, what's the best other? And that's like saying, on the surface, I fix one and I draw a line, and then I have a look at where the maximum is. So I can draw lines in one direction or in another direction. In one direction, it's called the geometric yield model, where I'm looking for the best V, and in the other direction, where I'm looking for the best, when I fix Tc, it's called the geometric yield model. When I fix V and I'm looking for the best Tc, it's called the tachometric yield model. Just don't worry about those names too much. And if I'm simultaneously looking for both, then I have to go to a surface like this and say, where can I maximize both? And if I'm constructing the geometric yield curve, then I can construct the geometric yield curve for different Tc's. In this case, in this diagram, the Tc's are called M. And I can analyze this, and then I can bring the cost into account, which I haven't at this point in time. And I can look for bionomic solutions and so on. But all I'm interested in this particular analysis is coming up to this point, and that is solving for the yield per recruit. And that is the yield per recruit has two interpretations. And one is it's what I get from a cohort recruited at a level N0 or R for all time in the future, or what I get from a common pool fishery or dynamic pool fishery here under equilibrium conditions, which assumes all individual cohorts have been recruited at the same level in the past and subject to the same harvesting strategy. Now, this analysis is like a first step to trying to find the best way to harvest a fishery. What should I choose for my optimal harvesting V, and what should I choose for my optimal TC, which is a reflection of the fishing gear. But what this analysis is missing is that how do I guarantee that I get the same recruitment every year? And if recruitment comes from the adults in my pool, if I harvest them too low, I can't guarantee I'll get that recruitment every year. So I have to make that connection. To make that connection, what I have to do is I have to build a model that has age structure in it. This model is kind of like an age structure model because when I go to the dynamic pool, I have individuals of different ages in there. But I haven't said how these individuals reproduce each other. I haven't said how the older ones create the younger ones. So that's a missing piece. So this model was built in 1954 with that missing piece in it. And then what people did later is they say, let's build more realistic models by looking at the reproduction rates of individuals of different ages. And so in order to do that, we're going to come to a topic later on, after the midterm, called age structure fisheries. But before we do age structure fisheries, we have to do a little bit about matrices. Because age structure fisheries require us to use matrices to represent our model. Because matrices are things that represent variables that have more than one dimension. Okay? Okay, that's it for today.